Chapter 9, Perturbation Theory, Dimensional Analysis, and Phenomenology. 9.1 Hamiltonian Perturbation Theory. In perturbation theory, we consider a known solution or system, typically a Hamiltonian description with its constants of the motion made clear, and we consider a small perturbation to that system. We then do a perturbation expansion for our solution by solving at various orders separately on what are simpler differential problems. See Ab. A. For some discussion and examples of ODE perturbation solution methods in general. Example 9.1. Perturbation theory involving a full Hamiltonian. Let's now consider perturbation theory involving a full Hamiltonian H of QPT. A simpler Hamiltonian with known solutions H sub 0 of QPT, and the perturbation part normal triangle H of QPT, where normal triangle H is much less than H sub 0. See equation 9-1. We expand all variables to various orders in a perturbation parameter, appearing in normal triangle H.
Consider the example of free motion with spring restoring force seen as perturbation. In this instance, we know the full solution without any perturbation theory, so can see how our result performs. So, for H sub 0 we have H sub 0 equals p squared divided by 2m, and for perturbation let's use the solution form for the spring potential in canonical coordinates. Normal triangle H equals m omega squared divided by 2 times x squared. We can then evaluate the Hamilton equations to get the usual result. See equation 9-2. Without any approximation. Treated as a perturbation, let's consider omega squared as the perturbation parameter. Thus at zeroth order we have p sub 0 equals 0 and x sub 0 equals p sub 0 divided by m. Thus, see equation 9-3.
Where we choose initial condition x of t equals 0 equals 0. Now, at first order we get, see equation 9-4, and see equation 9-5. If we now compare with the known full solution, see equation 9-6.
Through first order we can see exact agreement. If there is a time-dependent perturbation, then one often shifts from a Hamiltonian formulation to the Hamiltonian-Jacobi formulation. Consider the H equals H sub 0 plus normal triangle H setup as before, but now we have the added information of having obtained the principal function S, that is the generating function for the canonical transformation from the set QP gives the set alpha beta such that. See equation 9-7. In relation to H sub 0, the variables the set alpha beta are canonical and thus constants. In relation to H they will not be constants but will still be chosen as our canonical variables. Let the set P equals alpha Q equals beta. See equation 9-8.
Recasting to standard HJ form for perturbed Hamiltonian H with the time-dependent perturbation. See equation 9-9. And since Q equals the fraction with numerator partial differential H, and denominator partial differential P, and P equals negative the fraction with numerator partial differential H, and denominator partial differential Q, we get the exact relations. See equation 9-10. Exact solutions are often not possible, so we do perturbation expansions as before. Here, whatever values for the set alpha beta obtained at zeroth order are then used in computing first order as before. See equation 9-11.
And similarly for beta raised to the 1 power, and then iterated at higher order as needed. Exercise 9.1. Apply the H-shaped perturbation approach to the spring system considered previously, and reobtain the result in the H-shaped formalism. 9.2 Dimensional Analysis. Physics has dimensional quantities, unlike the differential mathematics used thus far, although one can introduce mathematical elements that can act as dimensional quantities. Dimensionless quantities can be grouped into products that are dimensionless. For example, the Stefan-Boltzmann law, described in, gives a relation between radiant energy E in a cavity, of volume V, with walls at temperature T. See equation 9-12. Physics mathematical formulas must have consistency on the dimensionality of terms. Example 9.2. A marble rolling in a circular orbit. Consider a marble rolling in a circular orbit inside an inverted cone. See reference 62 for more such examples, with half angle, from vertical, equal to theta. The variables for the system are then the orbital period tau, mass m, radius of orbit r, acceleration due to gravity g, and the aforementioned theta. Let's make a dimensionless product.
See equation 9-13, which is dimensionless if alpha minus 2 delta equals 0 and beta equals 0 and gamma plus delta equals 0, or simplifying we get beta equals 0 and gamma equals negative delta equals negative alpha divided by 2. Thus, we have the relation. See equation 9-14. With a lot more effort, a detailed analysis shows that f of theta equals 2 pi the square root of tangent theta. Exercise 9.2. Show that f of theta equals 2 pi the square root of tangent theta. A more general formulation of the partial solution possible by dimensional analysis is given by the Buckingham normal pi theorem.
9.2.1 Buckingham pi theorem. I. If an equation is dimensionally homogeneous, it can be reduced to a relationship among a complete set of independent dimensionless products too. The number of complete and independent dimensionless products n sub p is equal to the number of dimensionless variables and constants n sub v minus the number of dimensions n sub d needed to express the formulae n sub p equals n sub v minus n sub d. Clarification of the above methods is best shown with a few examples. Example 9.3. Pendulum dimensional analysis. For a pendulum with period tau, mass m, arm length L, acceleration due to gravity g. See the next equation, which has the same solution as before, but with no theta. Thus we have tau equals c the square root of L over g, where c is a constant. Exercise 9.3. Redo for horizontal spring motion on frictionless surface, one end attached, the other with a non-negligible mass.
Example 9.4. Nuclear blast analysis by G.I. Taylor. This is a famous example where the yield, energy, of a nuclear explosion was determined from a sequence of high-speed photographs that were published in a newspaper, with the necessary timestamps showing the spread of the blast. Let R denote the radius of an expanding blast wave. Let time from blast be t. Let the energy released be E, and let the initial atmospheric density be rho. Exercise 9.4. Show that E equals k rho r to the fifth power divided by t squared for some dimensionless constant k. Example 9.5. Consider the Hamiltonian. See the equation shown, for which the Hamiltonian equations give. See the next equation. We have our first conserved quantity, the energy, E equals h, and referring to the energy dimensionality, let's construct a table of terms.
Term order in Ex y 1/3 p sub x p sub y 1/2 d over dt 1/6 h1. We want a second conserved quantity w such that w can be constructed from xy p sub x p sub y xy p sub x p sub y, so as to give 0 consistent with the form of the building blocks above. Since the p sub x p sub y are the only place where terms are coupled, they must be in w. Since the p sub x p sub y are of order 2/3, we must have w of order is greater than or equal to 2/3. Also, w must be an exact differential, as with h. Case 1. Consider w to be order 2/3, this means that. See the equation shown. Where the coefficients are all constants we can choose. This expression isn't an exact differential for any choice of constants, however, so this case doesn't work. Case 2. Consider w to be order 5/6, this means that.
See the next equation. This expression isn't an exact differential either, so this case doesn't work. Case 3. Consider w to be order June 6th. Have terms like xp sub x and again no solution. Case 4. Consider w to be order 7/6. This works, but it recovers the first conserved quantity, the Hamiltonian itself. Case 5. Consider w to be order 8/6. Have terms like x squared p sub x and again no solution. Case 6. Consider w to be order September 6th. This works. The general form is now. See the equation shown. The general expression for w is now.
See the next equation. The general expression for w is thus. See the equation shown. Where the constant coefficients for each term are each separately equal to 0. There are thus 12 equations for the 11 unknowns indicated. Solving, we find that.
See the next equation. 9.2.2 dimensional analysis shows 22 unique dimensional quantities. If we start with the set of 6 fundamental dimensional constants, the set G epsilon sub 0 CEM sub EH, we find that there are 22 unique dimensionful groupings and 2 dimensionless groupings, the Eddington-Dirac number and the fine structure constant. In reference 45, we will again find 22 fundamental, dimensionful parameters are indicated. Exercise 9.5. Identify the 22 dimensionful groupings. 9.3 Phenomenology. When you don't have a fundamental theory but still want to establish a scientific model based on some empirical data of some phenomenon, then what you are establishing is a phenomenological model. A phenomenological model is not based on any first principles. Fundamental theories often start as phenomenological models until they are better understood. Feynman, in his descriptions of physical law, for example, describes the discovery process for physical law as enlightened guesswork. Thermodynamics is often viewed as a phenomenological theory that has borrowed physical law from elsewhere, such as conservation of energy. Partly for this reason, and awaiting other developments of the theory, discussion of phenomenology in the thermodynamics and statistical mechanics context isn't done until
some of the hardest problems in modern theoretical physics have been addressed in the form of phenomenological models: particle physics, condensed matter physics, plasma physics. If all else fails, try phenomenology. A famous example of this from the film Dark Star has to do with deactivating a thermostellar bomb that has accidentally activated. It's the semi-truck-shaped object. The bomb is controlled by an AI, and the crew has deemed their best chance to deactivate the bomb is to teach it phenomenology, so that it can see the big picture and realize it doesn't have to explode if it doesn't want to. Unfortunately, upon re-evaluating with greater perspective, the AI decides it is God, says, "Let there be light," and explodes. This is usually how things work out in physics as well, but that will have to await another day and another book. See the forthcoming for description of electromagnetism.